Okay, so today our Mathematician Spotlight is Rodrigo Treviño. I would have had a picture of Rodrigo on the screen, actually a picture of me with Rodrigo, but the power going out has killed the AV system in this room. So we don't have any pictures today, so sorry about that. So you will remember that I was gone last week because I went to University of Maryland to give a talk and also to do math with Rodrigo. So that's why I was gone. Rodrigo is a new assistant professor at the University of Maryland, College Park, and he studies ergodic theory, dynamical systems, geometry, and mathematical physics. So maybe you know what those words mean. You know what geometry means, you know what physics is, you know about dynamical systems because I talked about them a bit. But ergodic theory, what is ergodic theory? So I'm going to tell you what ergodic theory is. You can imagine that I have a video showing this, but you just have to imagine it. So ergodic theory measures how well mixed something is. And not necessarily something, but how well mixing a system is. So for instance, imagine I have a loaf of bread dough. Maybe it's like just whole wheat bread or something like that, or white bread. And I'm kneading it, right? You might ask, how well is this actually mixing the dough? Is it just sort of mushing it around, or is it actually mixing all the bits together? One way you could think about that is suppose I take a bit of like pumpernickel bread, like some kind of dark brown bread whose difference you can see. That's of dough, and I put it into my white bread dough. And now I keep kneading it. Now it's possible, so maybe the way you knead it is you knead it, and then you turn it a quarter turn, and then you knead it again, and you turn it a quarter turn. It's possible that that little bit of dark bread just kind of stays together. And in that case, you would say that this kneading system is not ergodic, because things don't really mix. On the other hand, it's possible that if I had a good kneading system, if I had a good kneading system, it might eventually get all mixed. So then the whole loaf of bread is sort of light brown. And in that case, you'd say it's ergodic. It might also be possible that because of my kneading system, it gets mixed in with one bit of the dough, and that part of the dough gets really mixed, but the other part just stays as white bread. And in that case, you'd say it isn't ergodic because it's only mixed in one area. So that's what ergodic theory studies. And you can see how this would be important and like really useful for a lot of things, telling if things become mixed. So the really cool video is of a taffy puller. Have you ever seen saltwater taffy being pulled? It's so cool. You have like this big machine that's like going like this and mixing all the taffy. And that is ergodic. If you have like pink taffy on there and you throw in a little bit of green taffy, it gets all mixed up. Yeah, questions or ideas? Yeah. Okay. I guess we can apply it to like Winter Storm Riley. Winter Storm Riley sure mixed things up. Yeah. Trees, power lines, roads, they're all mixed now. All mixed. It's interesting. So in the past two classes, we've been studying double integrals. So we've been computing the volumes under surfaces over rectangles. So we did that the first day, and then last time we talked about Riemann sums and how to precisely define these things. But it could be, amazingly enough, that you would want to integrate something that wasn't over a rectangle. So we talked about, like, suppose you own a granite quarry, and you want to know how much granite is in your quarry. Well, it's so great if your quarry is a square, but this isn't the way the world works. Often, the piece of land you own is not a square or a rectangle. So today we'll integrate over general regions. So for example, find the volume under the surface f of x comma y equals 2xy over the triangle in the xy plane bounded by the two axes and the line y equals 2 minus 2x. That's the quest. So the first thing to do would be to draw a picture. The claim is that the two axes and the line y equals 2 minus 2x bound a triangle. Who knows if that's even true? Let's draw it. So the axes, let me draw them in. Here they are, the x-axis and the y-axis. And the line y equals 2 minus 2x. Let's see, yeah, it goes like that. It starts at 2, because if x equals 0, you just get 2. And then it has a slope of negative 2. So there it is. And so if it starts at 2 and has a slope of negative 2, it hits here at x equals 1. Oh, okay, so the axes in this line, they really do bound a triangle. There it is. Okay, so we want to integrate over that region R, the function 2xy with respect to area. Okay, so we have two choices. We could integrate with vertical strips first, or we could integrate with horizontal strips first. Either one is okay. Let's do vertical. Okay, so we are, let's say, integrate in this order. So we would be fixing x. So we're going from y equals something up to y equals something of 2xy dy, and then integrate that from x equals something up to x equals something dx. That's the goal. Okay, so first, with respect to y, x is a constant. So we'll pick our favorite x. Maybe it's this one. And we want to go from here up to here, like the whole slice of this solid. Okay, maybe we should figure out what this thing will look like, actually. So this surface is 2xy. It's sitting over this. So when I pick an x, I'm taking a vertical slice through this solid. So let's just see what it looks like. When x equals 0, you're on the y-axis, the function value is 0. Can you see that? It should be 0. So it's sort of nailed down along the entire y-axis here. Similarly, when y equals 0, the function value is 0. So it's nailed down around the entire axis here. And the bigger that x and y are, the bigger the function value is. So here, when x and y are both positive, you get some positive number. So the surface should look something like this over it. You can see it? Okay. So we expect that we'll get a positive number, because the function is positive or 0 on the entire region. So it's not going to cancel out. It's not going to be negative. Okay, so we're taking this solid and taking a slice of it when x equals a constant. So for this, we want to know y goes from something to something. So y goes from something down here all the way up to something up here. I'm going to do this one. Y equals 0 at the bottom. So we go from y equals 0 at the bottom. And then how about at the top? Well, maybe I could say that y is 2, but y isn't always 2. Sometimes it's 2, sometimes it's 0. What y depends on x. So it's going to depend on x exactly the way this line depends on x. So can you say what it would be? Yeah, 2 minus 2x. Because this line is exactly 2 minus 2x. So the y values go from 0 up to 2 minus 2x. Okay, and now I want these vertical slices of my solid all the way from x equals this up to x equals that. So from 0 to 1. So some of them are big and some of them are small. And x equals 0 to 1, we'll get them all. So that's the setup. So we are not integrating over a rectangle anymore. If we had just said y equals 0 to y equals 2, then we would get this whole rectangle here. But we don't want it. We only want this part. And you might think, oh, I have a very clever idea. It would be a very clever idea. I will just integrate over the whole rectangle, and then I'll divide by 2. But remember, this surface, the bigger that x and y are, the higher the surface is. So if you integrated over this other part of the rectangle, you get a bigger number. The two integrals are not equal. So we actually have to integrate just over the one that we want. So we have to integrate just over this one. Okay, let's see how this goes. I mean, it's a little strange, right? Because one of our limits of integration is not a constant. So life is maybe going to be weird. Let's see what happens. Let's just see how it works. Okay, so let me copy the outer integral. X is going from 0 up to 1. And then of whatever's inside. Okay, the integral of 2xy with respect to y. Xy squared. Yeah, xy squared. Okay, xy squared. And I want to plug in from y equals 0 up to y equals 2 minus 2x. And I'll eventually be integrating that with respect to x. Okay, copy the outer integral. X is going from 0 to 1. So I have x times whatever y is. So x times 2 minus 2x, that thing squared, minus x times whatever y is 0. So actually, we don't have to, we're just subtracting 0. Dx. Okay. It's quite hard to integrate a thing like this, the best thing to do is to multiply out. So let's multiply out. Maybe we do some scratch work here. So x times 2 minus 2x times 2 minus 2x is x times, okay, I'm going to FOIL. So first is 4, inner, minus 4x, outer, minus 4x, last, plus 4x squared. Okay, and now I think I'll pull out a 4. My life will be easier then. So this is 4x times 1 minus 2x plus x squared. Is it okay? I think it's okay. Okay, so that's my integrand. Let's write that down. So the outer integral is x equals 0 to x equals 1. Maybe I'll pull the 4 all the way out of the integral, well, whatever. So now I'll multiply this out. So I get 4x minus, why would I, okay. Maybe I shouldn't have pulled out the 4. Shouldn't pull out the 4? I don't think so. I'll just multiply it again. So it might have made your life easier to pull out a 4, and it might not have. Whatever. Either one is okay. Let's keep the 4. So fine, minus 8x squared plus 4x cubed. Because the numbers are big, maybe this will work out nicely to have the 4 in there. Okay, either way is okay. We could have pulled the 4 out. Okay, so let's go in from x equals 0 to x equals 1. So this was unnecessary. Okay. Okay, let's integrate with respect to x. This, oh, I'm integrating. I don't need this anymore. Goodbye, integral sign. We do not, we are integrating. Okay, so the integral of 4x with respect to x is 2x squared minus 8/3 x cubed plus x to the 4th. So convenient. Okay, so that was a good reason to keep the 4, because we don't need any fractions. Going from x equals 0 to x equals 1. So when we plug in x equals 1 here, we get 2 minus 8/3 plus 1. And then we subtract off what we get when x equals 0, which is 0. Okay, so we won't subtract. Okay, and notice that 2 plus 1 is 3, which is 9/3. So this is 9/3 minus 8/3, which is 1/3. Okay. Okay, so, and we expected to get a positive answer because this function is either 0 or positive everywhere. So we're not surprised that we got 1/3. Sounds like a reasonable answer. Okay. So it was a little bit strange that one of our limits of integration is a function depending on x, but we just plugged it in like anything else. It was a little complicated because we had to square it, but we survived that and then just integrated it as usual. And then we got this volume. So this is the volume under c equals 2xy over our region, which is a triangle. Yeah. Questions or ideas? Yeah.
Would it have worked to integrate that from y equals 0 to y equals 2 and then from x equals 0 to a function?
Yes. Would it have worked to integrate from y equals 0 to y equals 2 and then from x equals 0 to a function? Yes. Shall we do it?
Okay.
Let's do it. Good idea. Okay, so let's try the other order of integration. So now we're going to use horizontal slices. It's on the page, it's just at the bottom. Okay, so now we're going to do the order where, let's see, y is on the outside. So y goes from something to something, and x is on the inside. X goes from something to something, and we are still integrating 2xy, but now dx, dy. So with respect to x, y is a constant, so we pick our favorite y. Okay, so here's a y. We're going slicing in this horizontal type direction, but again, we have this like solid thing, and we're taking a slice of it, trying to find its area. Okay, so for this y value, we're going from x equals something on the left over to x equals something on the right. And Vinay already said we should go from x equals 0 here on the left up to some function over here. So x is going from 0 on the left up to some function. Yeah. How would we figure out what it is? Yeah, just solve for x in terms of y. So we're on this line. This is the line y equals 2 minus 2x. That was y in terms of x, but we need x in terms of y. So let's solve. We have y equals 2 minus 2x, and we want x by itself. So let's put the x on this side. 2x equals 2 minus y, divide by 2, x equals 1 minus 1/2 y. So that gives us what x is in terms of y on this line. So x is 1 minus 1/2 y. So up here, x equals 1 minus 1/2 y. Yeah. And then we want all these horizontal bits all the way from y equals 0 at the bottom, all the way up to y equals 2 at the top. So we go from y equals 0 up to y equals 2. And now it's all set up. Okay. So as extra practice, we'll just do it. So, good. Put on our blinders here. The outer integral is from y equals 0 to y equals 2. The inner integral is 2xy with respect to x. So that's like x squared y. X squared y. Great. X squared y goes from x equals 0 up to x equals 1 minus half y. And then we'll eventually integrate that dy. So let's do it. So we go from y equals 0 up to y equals 2 of this thing. Okay, if we plug in x equals this function of y, we get 1 minus 1/2 y, quantity squared, times y, minus, what we get when we plug in x equals 0, which is 0. Okay, so dy. Okay, again, it's very hard to integrate things that are factored like this. So the best thing to do would be to multiply out. So we're going to integrate from y equals 0 to y equals 2 of, let's multiply this out. 1 minus 1 times negative 1/2 is negative 1/2. We have 2 of them, so I get 1 minus y plus 1/4 y squared times y dy. Okay, and then one more step to multiply out. So we're going from y equals 0 up to y equals 2 of y minus y squared plus 1/4 y cubed dy. Okay, so just to remind you what's going on, we integrated one step. So this is the area of the slice at this y value. At some y, depending on y. I should not say maybe this y value. Area of the slice depending on y. So you imagine we have this solid region that we're finding the volume of. We picked a certain y value and we sliced it. And so we're trying to know, like, whatever it looks like, what is the area of this slice here? Well, it's y minus y squared plus 1/4 y cubed. That's what it is. And now we'll thicken up each of those little slices with a tiny thickness dy so that this is a tiny volume, and then add them all up. So that's what we're doing. And we just chug, 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 and actually do it. So the integral of y with respect to y is 1/2 y. The integral of y squared with respect to y is 1/3 y cubed. And the integral of 1/4 y to the third, it's confusing, there's already a 1/4 there. But I think we get 1/16 y to the fourth. Okay, we plug in from y equals 0 to y equals 2. Okay, let's plug in y equals 2. Is there a squared here? I missed a squared. It's okay. Great, that's supposed to be a squared. Okay, so if we plug in 2 here, we get 1/2 of 4, which is 2, minus 1/3 of 8, which is 8/3, plus 1/16 of 16, which is 1. Which is the same thing as before. We actually had 2 minus 8/3 plus 1 before also. So it came out exactly the same way. So it's 1/3.
That's just a coincidence, right?
It's a coincidence that each of the bits came out the same, I think. Not a coincidence that the answer came out the same. That's a relief.
Also, do you have the tools to find these integrals without expanding? Like, can we do it with d substitution or integration by parts or any of the methods that we've been learning, or is it just a hard integral to solve it?
To integrate this without expanding?
1 minus 1/2 y to the fifth,
Oh.
for instance, and I don't want to sit down and expand everything out to integrate.
Yeah.
Did we do we have methods to figure out these integrals?
I don't think you have a method to figure out a general integral like this without expanding it.
Okay.
Expanding it is the easiest way. Just go slow and make sure you have approximately 30 people around to find your algebra error when you make it. Yeah, it's very helpful. If you're lucky, if you were going to take if you're lucky, the derivative of the inside is on the outside, and then you could do a u substitution. But in general, that will not be the case. Yeah, other questions? Okay, so it's a little bit strange to have functions in your limits of integration, but we have to have them because we're integrating over things that aren't rectangles. So when you're setting it up, there are a couple things you should do as sort of a sanity check. So suppose we have some double integral here of f of xy times or d, so with respect to some inner variable. So in this case, that inner variable was x. And then d, your outer variable. So in this second case, our outer variable was y. OK. Your outer limits of integration always have to be numbers. So these are always numbers. This one and this one. Always numbers. These inner ones could be numbers. So, OK, so for example, the ones are always numbers. As you can see, y here was going from 0 to 2. And in the other one, it was going from 0 to 1. They're always numbers, because you're just saying which values of your outer variable you want to collect your slices over. And that's just numbers. For your inner variables, they could be numbers. So for instance, here, x is 0, just starting at x equals 0. Or they could be functions. But they're always functions of the outer variable. OK, so it can't be like, if this was, first of all, if this was x equals some function of x, it wouldn't really make sense. But even if we didn't notice at that point that it didn't make sense, once we plugged in, we would now have something in terms of x. And our answer would be in terms of x. And that wouldn't make sense, because it's supposed to be a number. It's supposed to be some kind of volume.
But if we get an answer in terms of a variable, wouldn't that just mean that the volume is dependent on x and y?
If you got an...
Under the surface is dependent on the value of x and y.
So the volume of the surface is dependent on x and y, but you've set up which x's and y's you care about. In this case, it was like this triangular region. So once you've said which x's and y's you care about, your volume should be a number. Yeah. You could have said, oh, my surface is, it's not 2xy, it's axy. It depends on some variable. But that would be different. Yeah. So this is numbers or functions of the outer variable. Yeah. Yeah. So, good. OK. Good. So now what we'll do is just do a few more. So where interesting things happen, that's the goal. So see a few things that we haven't seen yet. So the first one is where both of the limits of integration are functions. So our next thing to do is to find the volume under the plane c equals 2y minus x over the region bounded by y equals x and y equals x squared. That's the goal. So the first thing to do is just figure out what's going on. Allegedly, there's some region bounded by y equals x and y equals x squared. Is that even true? Like if I had said y equals x and y equals 2x, would have been false. No region, no such region. But let's do it. So let me graph y equals x. Here it is, y equals x. And then y equals x squared. It's a parabola. Here it is. Okay, it doesn't really curve back along, but there we go. Good enough. Okay, so there's my region. So there it is. And then I have the plane 2y equals x sitting over this somehow. Okay, so good. So I want to find the volume there. Have to set it up. Okay, so we want to find the double integral over this region of 2y minus x dA. So let's first set it up in the horizontal direction. So if you pick your favorite y and take slices like this. So if we're picking our favorite y, that means y is on the outside. So y is going to go from something to something. And then x is going to go from something to something of 2y minus x dx dy. Okay, but now our goal is to find these limits of integration for this region. So x, so for our favorite y, x goes from here on the left over to here on the right. Okay, I will do the one on the left. This is the line y equals x. So whatever your y value is, the x value is equal to it. So this is x equals y. So the lower limit of integration is x equals y. Okay, how about this guy? What? Square root of y. Yeah, square root of y. Because this curve is, let me write it down here, y equals x squared, and we want to solve for x. So square root of y equals x. It would have been plus or minus square root of y, but the minus square root of y is the left side of the parabola. That's not the one that we're using. Okay. So x equals square root of y. And now we want all these slices from here to here. So you have to figure out these intersection points of the curves. So we have to find the intersection points. Of the two curves. Well, one of them is a line, but a line is a kind of curve. So we have y equals x squared and y equals x. So x squared equals x because the y's are equal. So x squared equals x squared minus x equals 0, x times x minus 1 equals 0. So x equals 0 or x equals 1. Okay, those are intersection points. So we have here 0, 0, and here 1, 1. You might have already known that. But if you had a more complicated function, you would have to solve for the intersection points. So from this, we know that so x equals 0 to x equals 1. So we're also going from y equals 0 so to y equals 1. Okay, so it's 0, 0 to 1, 1. So y goes from 0 to 1. Yeah, okay, okay. So now we have variables in both of our limits of integration. Yeah. Okay. So I happen to know that this one is a bit tedious to compute. So I think we'll hold off on computing that one and just set up the other one and compute it instead. So let's do the other one. So let's set it up in the other order. So then we would want to go from x equals 0 up to, x equals something to x equals something. We'd want to go from y equals something to y equals something of 2y minus x dy dx. Let's find the limits of integration here. So here, with respect to y, our x is a constant. So we're going to go pick a favorite x And we want the y's from there up to there. So y equals something up to y equals something. Can you figure out what it is? If you have an x value, can you figure out this y value? Yeah, it's x squared because it's on the parabola. And then down here, if you have this x value, what is this y value? Just x because it's on the line. So at the bottom, we want to go start at x squared and go all the way up to x. Something to notice here is that in some sense, these things switched. So for the horizontal slices, we went from the line to the curve. We went from the line to the curve. But for the vertical slices, we go from the curve to the line. Yeah, we go from the curve to the line. So which one is smaller depends on which way you're slicing. So be careful about that. Draw a picture.
If you make a mistake and you don't, like if the function is way too complicated to draw and figure out which one's the upper bound and which one's the lower bound, is it just you might switch the what they call it, the limits of integration,
Yep.
and you just get the opposite signed volume?
That's right. You just get if you switch them, you get the opposite sign volume. Same number, different sign. Yep. Yeah.
Right now, y equals x squared would always be less than 1 because it's like lower than 1, the limit.
That's true.
But what if we were doing y equals 2x? Then like halfway through would x squared be more than x?
Yeah.
So what happens then?
Right. We might have curves that intersect more than once. So you have to find all the intersection points and break it up into several integrals, making sure that the lower integral was always on the bottom, because otherwise you'd have like opposite, like negative areas canceling out with positive areas in a way that you wouldn't want. Yeah, good question. Yeah, nice. Yeah. Okay, and then x, let's see, we want to know what we want here, and we already found the intersection points, so x goes from 0 to 1. And now we would just compute this. So let's do this one. I didn't like the other one so much because it had a square root, but you can compute it yourself or look at the sheet. So let's do this one. X is going from 0 to 1 of, okay, integral of 2y with respect to y squared. I got that one. Integral of x with respect to y, xy. Okay. And we're plugging in from y equals x squared up to y equals x. So this is the integral from x equals 0 up to x equals 1. Y squared, when y is x, that's x squared. So this is x squared minus xy x cubed. X times x squared is x cubed, okay? Minus, let's see, what did I do wrong here? I should do the other thing first. Okay. Okay, so x is x squared minus x times x minus x to the fourth minus x times x squared is x cubed. Okay, this whole thing dx. So x squared minus x squared is nothing. Okay. So I'm going from x equals 0 up to x equals 1 of, let's just call this x cubed minus x to the fourth, so that everything has a good sign. Taking the integral with respect to x of x cubed is 1/4 x to the fourth. Integral with respect to x of x to the fourth is 1/5 x to the fifth. And we're going from x equals 0 up to x equals 1. So we get 1/4 minus 1/5. Have to have a common denominator. 5/20 minus 4/20 is 1/20. So that tells us that the volume, possibly the signed volume, there might be a negative part under this surface and above the xy plane is 1/20. Yeah. So the interesting thing that happened there was that we had functions for both of our limits of integration. And so when we plugged in, there were variables in all of the parts. And also that when we switched the order of integration, which one was on the top and which one was on the bottom flipped. questions or ideas? Okay. So in the last part of today, we will look at things where you have to break up the integral into two parts in order to write it down. So here's something to do. So find the area of the region between the lines y equals x, y equals negative x, and x equals 1. So first of all, allegedly, there is some such region. So we should draw a picture. Okay? Y equals x looks like this. Y equals negative x looks like this. And what x equals 1, I have to pick where 1 is. I say that it's here. X equals 1 looks like this. So, oh yes, there is a region bounded by those, and there it is. So we want to find the area of the region. Here's a clever trick. If you want to find the area of a region, all you have to do is take the integral over the region of 1 dA. Okay, so here's why that works. If you want to find the volume, suppose you have like a cylinder, right? It's a cylinder over a circle. The volume of the cylinder is the area of the base times the height. Okay, what if you have like a triangular base and you just have like a vertical thing? It's called a cylinder over a triangle. It's not a circular cylinder, it's a triangular cylinder. And you want to find its volume. Area of the base times the height. Yeah? So if you have like a cylinder, a thing where the horizontal cross sections are exactly the same at every height, volume is just the area of the base, or every cross section, times the height. So the clever thing is to just make a height of 1. So we're integrating the function f of xy equals 1. So if this height is 1, then the volume equals the area of the base. So we're going to find the volume here and really look at it as an area. So a volume of something with height 1 is just the area of the thing. So that's the clever trick. Okay, let's do it. So there are 3 ways, perhaps, to do this. So way number 0 is using basic geometry. Can you find the area of this thing? Yeah, 1, 1, 1. Yeah. So you can use either 1/2 base times height for this triangle, or you can just imagine you take this triangle and you put it there. And that would fill up a whole 1 by 1 square, which has area 1. Okay? So area equals 1/2 base times height, which is 1. So we expect to get 1. Another way we could do this is with vertical slices. So let's set that up. So if you pick your favorite x value, maybe it's this, we go from y equals something at the bottom up to y equals something at the top. Can you see what y is at the bottom? Negative x, yeah, the line is just y equals negative x, and this line is just y equals x. So we would be integrating from y equals negative x up to y equals x of the function 1, because we want to find the area, dy, and then we would integrate from x equals 0 to 1. Okay, x equals 0 up to x equals 1 dx. Okay, let's just do it. For the integral on the outside, x equals 0 to x equals 1. The integral of 1 with respect to y is y. And then we do y is x, down to y equals negative x. So we would get x minus negative x dx. So we would just get the integral from 0 to 1 of 2x dx, which is x squared from 0 to 1, which is 1. Okay, fair enough. Good. Yay. Now let's do horizontal slices. Goodness. Okay. So all you have to do is you pick your favorite y value. Like maybe this is my favorite y value. And you go from x equals something up to x equals something. I'll erase my scratch work for y. So on the left here, I go from x equals something up to here on the right, x equals something. It's supposed to be horizontal. What do you think? Here, x is negative y because y is negative x. And here, x is 1. OK, so let's set it up. Good. I hope you are getting slightly nervous, but I'm going to just let the tension build. So we're integrating from x equals negative y up to x equals 1 of our function, 1 dx. And then we're going, what y values do we need? Negative 1 up to, well, we want to go from y equals negative 1 up to 1. But these things sort of change at some point. Like my favorite y, I was lucky that it was down here at the bottom, because all these things kind of look the same. But then here something changes. So I can only really do this from y equals negative 1 up to y equals 0. And then I have to do something else. OK, let me get a third color. So this is the bottom part. And then we have to do something else for the next part. So if my favorite y value is here, for instance, then I'm taking a little slice here, where x goes from something on the left up to something on the right. So on the left, x is y, yeah, because this is the line y equals x, so they're equal. And on the right, x equals 1. So for the bottom, so for the top, we're going from x equals y up to x equals 1 of our function 1 dx. And then integrating that from y equals something to y equals something dy. OK, which y values does that work for? Here to here. Yeah, 0 to 1. So this, you might have to solve for this intersection value, but this is y equals 1. So this is going from y equals 0 up to 1. Yeah. So in this case, because our function is quite easy to integrate, just 1, there's no reason why we'd have to put it in a different order. But suppose we've seen functions where in the order you're given, it's impossible to integrate it. So you would have to put it in the other order, and then you'd have to break it into these two pieces. So this is the top. This is the bottom. So two pieces. And then you could integrate them separately, and we hope that we would get 1/2 for the first one and 1/2 for the second one, because the areas of each region is 1/2. Area of each region is 1/2. Yeah, questions or ideas? Yeah.
Can you explain again why we have to split it up into bottom and top?
Yeah, why do we have to split them into bottom and top? OK, so we were in this first one. I said x is going from negative y. It's kind of hard to see this negative y, so I'll write it again. Negative y. X is going from negative y up to x equals 1. Suppose that I integrated this from y equals negative 1 up to 1. Well, let's see. X is going from negative y. So here's the line x equals negative y. Let me come in with a different color. Do you have a favorite? How do you like orange? It is a great color. We're going from x equals negative y, which is this line, x equals negative y, up to x equals 1. Good, which is this line. So this is x equals 1, and this is x equals negative y. OK, and we're taking these horizontal slices from x equals negative y to x equals 1, negative y up to 1, negative y up to 1, negative y up to 1. And we're going to do that all the way from y equals negative 1 up to, well, maybe we should do it all the way up to 1. So then we'd be going all the way up here to 1. Oh, no, something has gone wrong. Yeah, because this line here doesn't define our region all the way from y equals negative 1 up to y equals 1. It only really defines our region from y equals negative 1 up to 0. And then for this top part, it's a different line that defines our region.
Could we have done it from y equals negative 1 to 1 and then subtracted off that extra region?
Sure, yeah. You could have gone from y equals negative 1 to 1 and then subtracted off the integral for this extra region. Sure. Yeah. But it would, again, have required two integrals. So sad. Yeah. Yeah, other questions or ideas? Okay, okay. So we can just look at one more region where different things happen. So in this case, both directions of integration need multiple pieces. So suppose, okay. So I'll just draw the picture for this one. So suppose you have the unit circle. Always draw your circle and then draw your axes. And your region consists of the left part of the unit circle, and then the line y equals 1, and then the line y equals x minus 1. Okay, so this is your region. So here's y equals x minus 1. Here's y equals 1. And here's the unit circle. So x squared plus y squared equals 1. That's what that is. And suppose we want to integrate some function over this region, this region. Well, you want to make your life easy. So you want to pick a direction where you can just set up one kind of an integral. So which horizontal slices or vertical slices? Which one can you set up just one? Yeah, horizontal slices. Yeah, if we pick horizontal slices, we're always going from the curve over to the line. Curve to line, curve to line, curve to line. Yeah. So in this order, we're going from x equals something to x equals something of our function. And then from y equals, I guess, -1 up to y equals 1. So x goes from whatever this is, I guess negative square root of 1 minus y squared, all the way up to y plus 1. But suppose you wanted to go in the other order, you'd have to have multiple bits. Because if we went on the left side of the y-axis here, we go from circle to circle, circle to circle. But on the right side, we go from line to line. So we'd have to set up two different integrals in order to make this happen. So pick whichever, if your function is easy to integrate, then pick whichever order makes one region. Maybe that makes your life easier. Yeah. All right. Thanks, everyone. See you next time.